So the member or element stiffness matrix, already I have derived this with respect to a plane truss element or bar element or spring element as well as the beam elements. So using slope deflection equations. Now I will derive the same stiffness matrix using different procedure, that is using our definition, basic definition of stiffness and flexibility. Already I have defined in my previous lecture, stiffness is nothing but the force required to cause unit displacement. When you give a unit displacement, then whatever the force required to cause that unit displacement, we define as the stiffness. So using that particular definition, let us derive the stiffness matrix of a beam element. So this is the second approach for deriving the stiffness matrix or member stiffness matrix. So as usual, you consider a beam element 1, 2 of length L and flexural rigidity EI with 2 degrees of freedom. That 2 degrees of freedom I just numbered at the ends with coordinates like this. I number it like this 1, 2, 3, 4. So in the previous derivation, I took this moment as the first coordinate, moment at the other end as second coordinate, and the 2 shears here as third and fourth. This I took it as Q1, Q2, and this as moment M1, M2, and I developed the stiffness matrix. Now I am using first, I will call shear as the first coordinate, rotation is there as the second coordinate, and likewise at the other end also I will just take it. It doesn't make any difference. Only thing is the position of that stiffness coefficients will be a little bit different in this stiffness matrix location. That's all. So consider a beam that is prismatic beam having uniform EI value. Consider a beam, prismatic beam of 1, 2 of length L and flexural rigidity EI as in figure with 2 degrees of freedom at each end. So the 2 degrees of freedom I am indicating by the coordinates as indicated by coordinates 1, 2, 3 and 1, 2 and 3 and 4 here. 1, 2 at the node 1, 3, 4 at node 2. So coordinate means it indicates the positive direction of either independent forces or independent displacements. So they indicate the positive direction. Here one means, so this is only one arrow that indicates the force or translatory type of displacement in that particular direction will take it as positive. Similarly here, rotation or movement in clockwise direction is taken as positive. That's what coordinate means. So next, to derive this stiffness matrix, so we have to give unit displacement in the positive direction. First you give 1 in the direction of 1 coordinate 1, like that you give a displacement d1 is equal, this displacement I will call it as d1 is equal to 1. So this is V1, this is theta 1, this is V2, theta 2 are the displacements. And the corresponding forces, we can call it as here Q1, here M1, here theta Q2, V2 or Q2. Displacement or force. Theta 2 or moment M2. Either Q2 or M2. They are the forces. Because force and displacement both are vectors. The positive direction of that force or displacement is indicated here. So to develop the stiffness matrix corresponding to these 4 directions, I will first go on giving unit displacement in the direction of each of these one by one, keeping all others fixed and determining the forces. So you can say we know the stiffness. We know the stiffness is defined as the force due to unit displacement. Unit displacement. Now here there are 4 coordinates, so naturally the stiffness matrix has to be 4 by 4. Since we have 4 coordinates, 4 coordinates corresponding to 4 independent displacements at the ends of elements, that is V1, theta 1, V2, theta 2. They are the displacements. V1, theta 1, V2, theta 2. And 4 displacements at ends 1 and 2 of the element. So their positive directions are indicated. Since there are 4 displacements, 4 coordinates, size of stiffness matrix is 4 by 4. That is, that Km is nothing but this K11, K12, K13, K14, K21, K22, K23, K24, and like that K31, K32, K33, K34, then 4th element, 4th row element, 4-1, 4-2, 4-3, 4-4. So it is a 4 by 4 element. That's what I have told. Stiffness matrix size is 4 by 4. That is number stiffness matrix that I have to develop. How to develop means I have to use the definition. Stiffness is defined as the force due to unit displacement. Force developed due to unit displacement. You go on giving unit displacement along each of these directions. First, along direction V1, you give a unit displacement like this. Then, whatever force required, since I am giving displacement like that, there must be a force in that direction, and that force I am calling it as K11. That force is nothing but 4 EI by L. Not 4 EI by L, it is 12 EI by L cube. Now, this element has to be in equilibrium. When I give a unit displacement, due to that unit displacement, there must be a force equal to 12 EI by L cube. To keep this in equilibrium, here there must be a force equal and opposite, and that should be when we have a cube to satisfy equilibrium requirement. Sigma V has to be 0. And this force is nothing but your K3. It is the force developed along coordinate 3 when unit displacement is given along 1. That is the thing. So this Kij is nothing but force along I due to unit displacement along J. If you give a unit displacement along J direction, whatever force developed, it is called I, K and J along I direction. Here I am giving a unit displacement in the direction of 1, force developed in the direction of 1 is K11 because displacement is also in the direction of 1, force is also in the direction of 1. Here force is in the direction of 3 when displacement is given in the direction of 1. So this force we can get by equilibrium requirement because this force, standard one, whenever you remember always, whenever I give a unit translated displacement delta at one end, then the force required there to give that displacement delta is given by LVI delta by L square, L cube. If EI and L dot, the length and rigidities. And here it should be equal and opposite. So this gives a moment in the anti-clockwise direction. There must be a moment here in the clockwise direction, and that moment is 6 here by L square. You can remember. And similarly, if I give a unit rotation at one end, then due to this unit rotation or rotation theta, then the force required will be 4 EI by L into theta. Here the force will be 2 EI by L theta, half of that particular value, and this gives a clockwise rotation. To keep it in equilibrium, there must be equal and opposite reactions which are nothing but 6 EI theta by L square here. So now this is perfectly in equilibrium. Here also this moment 6 EI by L square. So to keep this in equilibrium, these are values. That value you can remember those two due to translation at one end, what are the forces developed at all other coordinates, and due to rotation theta, what are the forces that remembering those values you can develop the stiffness matrix coefficient using this notation K for denoting the stiffness coefficients. Kij is defined like this. So here for the first coordinate it is this value. To keep this in equilibrium, this gives a clockwise movement. Here there must be anti-clockwise movement like this, and this anti-clockwise movement will be 6 EI by L square because I have shown 6 EI theta delta by L square. This delta will be 1 there. That's why it is 6 EI by L square here. Here also it is 6 EI by L square. So this is anti-clockwise, this is also anti-clockwise. So they are negative quantities, and this is nothing but K41. This is nothing but K21 as per this definition. It is the force along 2 when unit displacement is given along 1. So you have developed K11, K21, K31, K41. That is this. K11, K21, K31, K41. The first row of that stiffness matrix element we have developed by giving unit displacement along one coordinate 1 and finding out the forces at all that 4 coordinates. So next you can give along 2 unit displacement, 2 in the clockwise direction, like that. You give unit displacement. So there must be a force here, and that force from this, if you give a displacement theta, force is 4A by L theta. If you give a displacement 1 here, force will be 4A by L. Here also it will be half that value and in the same direction, that is 2A by L. So these two will be 6A by L, and here the reactions developed will be resisting this moment, and this gives clockwise moment, resisting moment will be in the opposite direction, that is like this. So this gives a total moment of 6A by L. Here this reaction also should give a moment of 6A by L, and therefore this reaction will be 6A by L square. That's what I told. 6A theta by L square. Theta is 1 there, so it is 6A by L square. This is also 6A by L square. And as per this rotation, this is the displacement corresponding to coordinate 2 when unit rotation is given along 2. So this is the rotation along direction of 4 when unit rotation is given at 2. This is translation along direction of 3. So 3 direction, not 3, this is along direction of 1, which is like this. This is opposite, so this is negative. So this will be along direction 1 when unit displacement is given along 2. So this is nothing but it is in the direction of 3 when unit displacement is given along 2. So K12, K22, K32, K42, that is the second row, second column we have generated. By just remembering, by giving unit translation, what all the forces develop. By giving unit rotation, what all the forces develop. By just remembering that 12A by L cube, 6A by L square, and rotation 4A by L, 2A by L, 6A by L square. Remembering those figures, we can develop this stiffness matrix. This is the second procedure. Likewise, this, by giving a unit translation along 3 direction, we will give unit translation, keep all other displacements fixed, don't allow all other displacement. Whenever you give displacement only along one coordinate at a time, then you can superpose by principle of superposition, which already I have told. So this is exactly the principle of superposition I am using. By giving unit displacement, I have found out what are the forces due to individual cases, and I can add it to find the combined effect for the entire structure by giving unit displacement at all other coordinates. So here, when you give unit displacement on similar lines, here force required will be 12 PI by L cube. Here you should be equal and opposite from equilibrium criterion. That's very, very important, equilibrium criterion. That directions I have shown. In the direction of displacement given, force should be in that direction. To keep this in equilibrium, here it should be equal and opposite. So this gives a clockwise movement, anti-clockwise movement. To keep it in equilibrium, here moments develop will be in the clockwise direction, and that moments will be here 6 by L square. Here also it is 6 by L square. So this is nothing but this force along 3 when displacement is given along 3. This is force along 4 when displacement is along 3. This is force along 1 when displacement is 3. So this force is negative and this is positive, this is negative, this is positive, and this is clockwise, clockwise, positive, clockwise, clockwise, positive. Here, like this, it's okay. Here it is anti-clockwise, so negative, negative. I have already given anti-clockwise potential. So this is K43, K13, K33. This will be along direction 2 when force is around 3. Okay. Then last case, this around direction of 4, that is here, this is 4. You have to give a unit rotation, that is the fourth coordinate. In that direction, clockwise direction, I have given unit displacement, keeping all the time displacements fixed. So there must be a moment here, and that moment will be 4 here by L. Here, it should be in the same direction. How that value, that is 3 here by L, it is giving a clockwise moment. To keep it in equilibrium, there must be anti-clockwise moment, and that creates here equal to 6 here by L square, 6 here by L square. Now, these are the forces developed due to this unit displacement, and these forces, this force is along 4 direction when displacement is given along 4. So this is the force along 3 when displacement is given along 4. This is minus, of course. This is force along 1 when displacement is along 4. This is force along 2 when displacement is along 4. So K24, K14, K24, K34, K44. That is this fourth row. So therefore, your Km, that is element stiffness matrix, I can write it as from the first one, K11 is L by L cube. Next, positive direction. Next, K12 is minus 6CL by L square. K21. Then K31 is minus 12CL by L cube. This is plus, this is minus. Minus 12CL by L cube. Then 6CL by L square, that is minus 6 here by L square, 4. First row, second row, third row, fourth. Or first column. So then second one, this case, K12 is minus 6 here by L square. Then K12, this is K12 is minus 6 by L square, K22 is 4 by L, then K32 6 by L square, then K42 2 by L. Then this third case, K13 minus 12 by L cube, then K23 is 6 here by L square, 6 here by L square, then K33 12 here by L cube, then K43 6 here by L square. Then in this north case, K14 minus 6 here by L square, K24 2 here by L, then K34 2EL by L square, then K44, it is 4EL by L. This is the stiffness matrix. It has been generated by giving unit displacement around each of the coordinates one at a time and evaluating the forces. Remembering for the standard case by giving a unit, giving a displacement delta, rotation theta, what are the forces. Remembering this case, so you can develop that, and that gives you the element stiffness matrix. Or this you can write it by taking 2 EL by L outside. Yesterday I derived this. This is nothing but 6 by L square. This is minus 3 by L. This is another way of writing that same stiffness matrix. So this is 6 by L square minus 3 by L. So it is symmetric. This is minus 3 by L, minus 6 by L square, minus 3 by L. This is 2. Then this is 3 by L. This is also this 3 by L. This is 2 by 2. 2EA by L I have taken outside. So this will be 1. So here by symmetry, it is 3 by L, 1. Then this is 6 by X square. This is 3 by L, 3 by L. This is the element stiffness matrix corresponding to coordinates 1, 2, 3, 4. I have numbered here. 1 for the shear, 2 for moment, 3 for shear, 4 for moment, or translation, rotation, translation, rotation. Therefore, we can write these forces as Q1, M1, Q2, M2. They are nothing but this Km 2EL by L into this matrix, that is 6 by L square minus 3 by L minus 6 by L square minus 3 by L, and it is 2, 3 by L, 1, 6 by L square, 3 by L, and 2. This is symmetric. Into the corresponding displacement V1, theta1, V2, theta2. So it is the force displacement, independent displacement through the matrix that we define as member element stiffness matrix. So this is another method of arriving at the member or element stiffness matrix. So yesterday I derived it, same equation, of course, by taking M1, M2, Q1, Q2. Instead of that I have taken now, order I have changed, Q1, M1, Q2, M2, that's all. It is all same value of coefficients will get corresponding to that. And this is by usual definition, knowing the definition of stiffness, so you can develop the element stiffness matrix for a beam element. So this can be done. So now truss element also on similar lines you can derive. So you can, if you club the element stiffness matrix of a truss and a beam, you will get the element stiffness matrix of a rigid plane frame member, which you can use for your analysis of rigid plane frame using stiffness method. So that's how. So this you can remember. Generally, we adopt this procedure in Unit 3 for solving continuous beam, plane frame and truss problem. This is the procedure we follow. That's why it has derived the stiffness matrix from this particular thing also. Method also. So next, we can derive the stiffness matrix of a bar element also having length L, AE, axial rigidity corresponding to the coordinates 1 and 2. We can derive one similar lines with 2 degrees of freedom. So the stiffness matrix is nothing but AE by L 1 minus 1 minus plus 1 corresponding to these coordinates. So on similar lines you can derive. So next, this is for X element. This is Km member stiffness matrix. Km for a plane truss element. This is one plane beam element I have told. Then Km for rigid plane frame member. So that is, if you consider the rigid plane frame of length L, flexural rigidity EI and axial rigidity JE, because plane frame member is subjected to an axial force, shear force and bending moment. Axial force, shear force, bending moment. All the three I have plus the two matrices. So this I will take 1, 2 coordinates, axial force, then shear 3, moment 4, this 3, 4, 5, 6. So for this, you can write this stiffness matrix as like this, corresponding to coordinates 1, 2, 3, 4, 5, 6. It is a 6 by 6 matrix. For truss, it is 1 by 1. For beam, it is 4 by 4. For plane frame, it is 6 by 6 matrix. So we can write the elements in this fashion. Like this. So for plane frame truss, it is EA by L, AE by L and minus AE by L minus AE by L. This is AE by L plus. And all others, it is 0. This is for that truss element, because I told you stiffness matrix is always symmetric. First row, first column, symmetrical. Second row, second column, symmetrical. So that. Then for beam, just now I derived, so that is 12 EI by L cube, then minus 6 EI by L square, minus 12 EI by L cube, and it is 6 EI by L square. That it is symmetrical, minus 6 EI by L square, minus 12 EI by L cube, minus 6 EI by L square. Then you have here 4A by N, then 6A by N square, then 2A by N. 6A by N square, 2A by N. Then 12A by N cube, then 6A by N square, 6A by N square, which is 4A by N. So this is the stiffness matrix of a rigid plane frame element, which is nothing but combination of truss element and a beam element. It's very simple. To remember, first you have to remember truss element which I derived, that is AE by L minus AE by L. This whatever I have written here, AE by L I have taken outside, that I have taken inside here, that's all. And all others, 0, all other coordinates, that is vertical rotation, they are all not contributing in truss element. And in the beam, only axial deformation is not there in the beam. Others, stiffness coefficients will be there, and that is this. So combining this truss and beam elements, you will get the stiffness matrix of a rigid plane frame element. So if they ask you to derive element stiffness matrix for a plane frame element, first you have to derive stiffness matrix for this axial force, then shear moment you have to derive, and you have to plug the two, you will get the stiffness matrix for rigid plane frame element. So now I have defined what is meant by element stiffness matrix and what is the value of the element stiffness matrix for a bar, truss or spring element, what is the stiffness matrix for beam element, what is the stiffness matrix for plane frame element. All these cases I have derived. So by deriving stiffness matrix for a grid element, you can on similar lines, grid element is similar to, which is subjected to torsion as well as bending. The stiffness matrix for torsion, it is similar to axial force. Instead of axial force, you will get axial moment, and the value of that torsional contribution stiffness, it will be Gj by L. Instead of Ea by L, you will get Gj by L. And of course, bending it is same as beam element, so you can club torsion as well as bending together. And if you club all these put together, you will get stiffness matrix of a space frame element, of course, which is not there in syllabus. Only you have beam, truss, and rigid plane frame, for which the derivation you can remember. Whatever I have done, you can remember and do it. So next, you will take up flexibility, element flexibility matrix of a member. Flexibility matrix of a member, or element flexibility matrix, Fn. That is Km, this is Fn. So as I told you, already I have defined what is meant by flexibility matrix of a member, which I defined as before displacement produced due to unit force. So if you have number of system of forces, independent forces, then that relationship between force and displacement is through this flexibility matrix. First I will define, as I defined stiffness matrix, you can define flexibility matrix also like this. Flexibility matrix of a member or element is defined as the relationship. It is defined as the relationship between we define a relationship between independent forces at the ends of independent forces at the ends of members and independent forces at the ends of members and the corresponding net or relative displacements corresponding to net or relative displacement at the ends of so it is a relationship between the four independent forces at the end to the net displacements, whereas stiffness is the relationship between independent displacements and the forces, which I derived now. This Q1, M1, Q2, M2, that's the independent forces, or this is independent displacements, V1, theta 1, and V2, theta 2, and the relationship between the end forces and independent displacements through a stiffness matrix. Here it is independent forces. Independent forces will come on the right side, displacements will come on the left side. As I derived in the previous class already, from slope diffraction equations, for example, consider a prismatic beam member of length L and capsular rigidity VI, and the member ends are 1, 2, and having degrees of freedom is 1, 2, 3, 4. With 4 degrees of freedom like this at the two ends. So beam member 2 with 2 degrees of freedom at each end as that. We know that the forces and displacements corresponding to coordinates, that is degrees of the coordinates 1 to 4 B, Q1, M1, Q2, and M2, and displacements theta 1 and that's V1, theta 1, V2, theta 2, corresponding to these coordinates 1 to 4. Forces corresponds to coordinate 1, Q1, 2, Q1, M1, Q2, M2. Similarly, from 1 to 4, displacements are V1, theta 1, V2, theta 2. That's what I told here. Here it is Q1 and V1. Here M1, theta 1. Here Q3, V3. Here Q4. This is Q2. Which is M4, theta 4, Q2, V2, Q1, V1, M1, theta 1. This is theta. So V1 theta 1, V2, theta 2. They are the displacements Q1, M1, Q2, M2. They are the forces. Forces and displacements corresponding to these coordinates. They indicate the positive direction of forces and displacement. It is there. Then we know from slope deflection equation, slope deflection equations, M1 is given by 2 by N, 2 theta 1, theta 2 plus 3 V2 minus V1 divided by N, and M2 2 by N. This already had derived in the previous plus 2 theta 2 plus 3 into V2 minus V1 by N. There I derived for stiffness matrix, now I have derived for flexibility matrix. Then you know from this slope deflection equation like this, 1 and 2, also you know Q2 is nothing but M1 plus M2 divided by N. So Q2 equals M1 plus M2 by L means you add these two, you will get 2 by L into 3 theta 1 plus 3 theta 2 plus 6 V2 minus V1 by N. You see that Q2 and Q1 is nothing but minus Q2. Sigma 2 equals 0, sigma V equals 0. This is sigma M about the point 10. I have taken sigma H is 0 is not coming. Equilibrium requirement. From deflection equation for equilibrium requirement is Q1 equals minus Q2, that is Q1 equals 2 by N into minus 3 theta 1 minus 3 theta 2 plus 6 into V1 minus V2. This minus, instead of writing minus 6 into V2 minus V1, I will write it plus 6 V1 minus V2. It's all same. So if I do like this, these are the 4 equations available satisfying the equilibrium condition and also moment relationship. Out of this, now I have defined flexibility matrix as the relationship between independent forces and the displacements. I have here the 4 displacements which is always independent. The corresponding forces, they are not independent, because you are seeing here Q1 is equal to minus Q2. That means Q1 and Q2 are not different, they are one and the same but of opposite side. Similarly, Q2 is sum of the moments divided by L. So again, this is not independent. It depends on M1, M2. So out of these 4 forces, only 2 forces are independent. Which are those 2 forces? Either it can be M1 and M2. If I determine M1, M2, if I treat M1, M2 as they are known, then from this relationship you can determine Q2. From this relationship you can determine Q1. Q1 equals minus Q2. For Q1 and Q2 you can determine only determining during analysis M1, M2. Either you can choose M1, M2 as independent or Q2, one of these M2, you can treat it as independent. So Q2, M2, if you treat it as independent, M1 you can determine from this relationship, Q1 you can determine from this relationship. So out of 4 forces, N forces, out of 4 N forces, only two forces are dependent or independent or independent. This already I have concluded even in previous class. So say either M1 and M2 or Q2 and M2 or Q1 M1 also you can select it. So therefore you have three or two flexibility matrices, so which gives you the relationship between the independent forces and the displacement. Whereas in stiffness matrix it is only one relationship, that is all the four displacements are independent, only one relationship here you have. Whereas here in flexibility it is the two independent displacement, more forces are there, you can have two independent flexibility matrices. That's why I told flexibility matrix is a little bit tedious. It is not a constant value, difficult to write a common procedure to identify for solving the problem. So because here you are seeing, you can select either this or this as independent forces. So let us selecting M1 and M2 as independent forces. We have M1 is equal to 2EI by L into 2 theta 1 plus theta 2, and M2 as 2EI by L theta 1 plus 2 theta 2 from this relationship. V1, this M1, M2, Q1, Q2, I don't treat it as independent because Q2 is given by M1 plus M2 by L and Q1 is equal to minus Q2. You have from these two relationships, Q1, Q2 can be determined the moment you select M1, M2 as independent. So M1, M2, you can get it from that particular equation. So now you solve theta 1 and theta 2 from this. You will get a relationship between the independent forces and the displacement. So that is nothing but our flexibility matrix. So solving for theta 1 and theta 2. So how to solve for theta 1 and theta 2? So this, I will write it like this: L by 2EI into M1 equals 2 theta 1 plus theta 2. This I can write it as L by 2EI M2 is theta 1 plus 2 theta 2. I call this as equation A, equation B. If I multiply the equation B by 2, I will get L by Gi into M2 is equal to 2 theta 1 plus 4 theta 2. And multiply this B by 2. Now I will subtract this C A. So C minus A. If I do, then L by L by EI into M2 minus M1 by 2 is equal to 2 theta 1, 3 theta 1 cancels. You have here 3 theta 2, 4 theta 2 minus theta 2. Therefore, this theta 2 is nothing but L by 6EI into M2 minus M1 by 2. This is what you got. So substitute this in any one of these equations, you will get theta 1. Or you can solve that also. So you multiply this a by 2. If you multiply by a by 2, you will get L by ei into m1 is equal to 4 theta 1 plus 2 theta 2. We call this as b. Then we subtract from this b, the equation, we subtract d minus b. D minus b, if you do it, then L by ei into, here also thinking, C minus A, that is L by ei, M2 minus M1 by 2, C minus A, M1 by 2. Here on similar lines, D minus B, L by ei, M1 minus M2 by 2. Here it is M2 minus M1 by 2. Here it is M1 minus M2 by 2 is equal to 3 theta 1. That is 4 theta 1 minus theta 1, 3 theta 1, 2 theta 2 theta to cancel. Therefore, you have this theta 1 is nothing but L by 6 ei is 2M1 minus M2. Here, that is, this is 2M2 minus M1. This 2 LCM 2M2 minus M1, that 2 is here. This 3, if I go take it by bottom, will get 6. So these are the values of theta 1 and theta 2. That's what I have told here. Solving for theta 1 and theta 2 will get this. Therefore, you can write the matrix form theta 1, theta 2 is nothing but L by 6ei into 2 minus 1 minus 1 2 into M1 M2. This is the relationship between the independent forces. Selecting M1, M2 as independent. The relationship between the forces, M1 independent forces, that's what I told you. It is the relationship between independent forces, M1, M2, and the corresponding net displacements, theta 1 and theta 2 are the displacements corresponding to this. And this is that relationship, and this we call it as the flexibility matrix. So this is displacement, nothing but Fn flexibility matrix into the force P. So this is Fn is flexibility matrix. For this beam element, flexibility matrix is nothing but L by 6ei into 2 minus 1 minus 1 2, treating M1, M2 as the independent forces. If you select this Q2 and M2 as independent, then you will get another flexibility matrix. Of course, on similar lines, you can derive that flexibility matrix also. But I told you in the previous class, let us always treat these moments at the joints or ends of the members as the independent forces. So it is easy because the transformation from local to global coordinate doesn't arise because moment, it is about the local and global coordinate, it is same moment about z-axis, it is same for all planar structures. So that is, so this is about the definition of element flexibility matrix. So element flexibility matrix for B member I had derived like that. For truss or plane truss member already the stiffness matrix is A by N 1 minus 1 minus 1, 1, and I told always the flexibility matrix is inverse of stiffness and they are converse of one another. So flexibility matrix of this truss element or bar element, you can take inverse of this, that is L by AE minus 1, 1. You can treat this as the inverse. So minus 1, 1 and so that is, and between these two you will get CT plane 3 member. Again, remember we are treating end moments as the independent forces. So this is about generation or development of member flexibility matrix and concepts of stiffness and flexibility which we use extensively in our analysis of plane frame structures. So next we will talk about the relationship between the local axis and global axis and conclude it. So now we will talk about what is known as principle of contraperiodians, or to find the relationship between global and member stiffness matrix. Because as already I told, the member or element stiffness matrix always is derived with reference to the local coordinate system. Local coordinate system always consists of the member axis as one of the axes and other two axes now perpendicular to this as the other two coordinate axes. So this we call it as local coordinate system, whereas the global coordinate system is our usual conventional orthogonal coordinate system wherein horizontal axis is always treated as one axis, another two normal to this are treated as the other two axes. So this is local axis, this is global coordinate system, wherein one of the axes is chosen as horizontal and other two perpendicular to this, we choose it as the other two axes. Always this coordinate system consists of three axes. Horizontal is treated as one of the axes and other two normal to this are treated as the other coordinate system. That is global or system coordinate system, and this is local coordinate system. All of our loads, everything which we come across in day-to-day practice, they are all with respect to global coordinate system, and also the displacements, everything, whatever we get, they are also in the global direction. Then only it is easy to apply the equations of equilibrium condition. Whereas just now you saw we derived the member property, that is stiffness matrix as well as flexibility matrix with respect to local coordinate system. That is treating member axis as one of the axes and other two are perpendicular to that. And with reference to this coordinate system, that is degrees of freedom, everything, we took with reference to this local coordinate system and derived that element and stiffness matrix as well as element flexibility matrices. But now problem is loads will be in global coordinate, whereas these properties will be in the element coordinate system. So we have to find a relationship between the global and local. So we have to transform these values from local coordinate system to global and do the analysis only with respect to one coordinate system. Again we can convert it into either local or global outwards and using what is known as a transformation matrix. So either force transformation matrix or displacement transformation matrix, we can use it for finding out, for converting global to local coordinate system. So this will be done using a principle called principle of contravariance. Now we will state this principle. So consider a system of forces. Consider two systems of forces and displacements in local and global coordinate systems. Consider two systems of forces and displacements in local and global coordinates as related to each other as below. So, you know that force displacement relationship. So, in global coordinate system, I will say Fs is equal to, so the global stiffness matrix into this global displacement. This is 1. F equals Kd. This is what I define. F is nothing proportional to D, or force is P, I use the notation. P is proportional to D in elastic limit I told, or P is equal to Kd, where K I define it as the stiffness. So let this force displacement relationship P is equal to Kd, let us define with respect to this global coordinate system as Ps equals Ks and ds. Another system with respect to local coordinate, the Pm is the system of forces and Km is the member flexibility and Dm is the displacements corresponding to local coordinate system. So I have defined here two coordinate systems, global and local, and with reference to these two coordinate systems, the force displacement relationship I have indicated like this from definition through the stiffness matrices. One defined with respect to local axis, global. This already I defined. There are local coordinate system, how to derive the stiffness matrix that you have already seen. Now I will convert it to global. So this stiffness matrix into global coordinate system I have converted. So that is my main object or main problem now, which I am doing by principle of contravariance. So the force displacement relationship is given by this. Now I will say let the forces in global and local coordinate systems, local coordinate system be related as this PS system, let it be related as, I say, PS is equal to some R into PM. So either I will consider instead of matrix, I can say, or one system I can take it, KS, DS. This as 1, this I can write it as PM equals KM, EM. One of quantity I consider. Here also, one of quantity. Let this PS and PM be related through this relationship where that all is called transformation matrix, force transformation matrix. So that is the matrix which transforms the system forces to member forces. I don't say this matrix because I am using only one single quantity. I'll say R in the force transformation. Force transformation or force measurement matrix. It can take one by one matrix is also possible. So I can use the by matrix or that. So then we have work done. With external work done, we have external work done will be stored as internal strain energy in the structure. So this external work done is nothing but the force into displacement PS ds t. Because PS and ds they are of same order. When we have to multiply two matrices of same order, then I have to take one transpose of the other. Because for multiplying two matrices, column of one should be equal to row of other, or vice versa. Row of one should be equal to column of the other. Then only multiplication is possible. So that's why I am using here when the matrices are of same order. So one I have to take transpose of the other. So work done is nothing but force into displacement. So in the global coordinate system, work done is PS into ds or PS into dst I have to write. And in local coordinate system, it is PM, PMT on similar lines. So this work done has to be same because it is stored as internal strain energy, whether it is local coordinate system or global coordinate system, it doesn't matter, energy should be same in both the systems. So this is another relationship I have. So totally 4 relationships I have. From this, now I can relate the global and local coordinate system. That's all. One, the force displacement relationship in the 2 coordinate systems I have considered, and another work done, since it is same in both the systems, I have considered another equation. Another, the force in local and global coordinate system, it is let it be related to this member coordinate system by a transformation matrix. I told you that is another thing I have considered. Now, using this, so we can say from 3 and 2, and getting like this, PS is equal to R into PM. PM from 2 is given by Km into dm. PS equals RPM. Instead of PM, I will write it Km dm. Like this. Now PS is equal to RKM dm. This dm, this Km. Km is what PM is this. PS is this. RPM. Yes, dm. This PS from 1. PS is nothing but KS, DS, PS is nothing but KS, DS is equal to R, KM, DM. That's what we got. Is KS. One second.
Yes.
So we will consider this 4th equation. Now, from 4 is PS dST. This PS is nothing but from 3 and 4. 3 and 4 I will use it. Instead of PS, I will write RPM. PS is equal to RPM, that I write here, into ESP is equal to PM DMT. Right? The R, this PM, EPM get cancelled. I have RDSP is equal to DMT. Or I can write DS is nothing but DM is nothing but RDS. Either RDSP equals DMT or DM is equal to RTDS. This relationship is RTDS. Same RT. This is one relationship. We should remember using this relationship. Now whatever I have derived from this work done as well as the force displacement relationship force in global and global coordinate system, local coordinate system, that relationship and well done. By using that, I have arrived this relationship, the displacement in local and global coordinate system is related by again this R T value like this in this fashion. Now I will substitute this in equations 1 and 2. So from 1, 2 and 5. From 1, 2 and 5 I can write it from 1 KS DS, from 1 KS DS, that is from 1, 2, 3 and 5. All this put together. I can write 1 PS as KS DS is equal to or PM is nothing but KM DM from 1, 2 and 3 and this from 1, 2, 3 we have KS DS is equal to or KM DM. It's okay, PM is equal to MDM from 1, 2 and 3. Now I will use this from 5. From 5 I can write it as KS DS is equal to or KM DM is nothing but RT DS. This is from 5. I can use it. This DS cancels. So therefore, I will get therefore KS is nothing but R KM RT. This is so this particular thing it relates global stiffness matrix to local stiffness matrix. Here, the global displacement to local displacement. It is related with RT. The global stiffness matrix related to local stiffness matrix. Again, it is related by R and RT. This. So this is called principle of ontology, which relates the global and member stiffness matrices. That is this equation. So using this relationship, always since I have derived Km already for plane 3 member, truss member and beam member, I have derived Km values and finding out, that is nothing but finding the relationship between the forces in local and global coordinate system. If I relate the member forces and global forces by a transformation matrix, that if I determine transformation matrix, I can always convert the member stiffnesses matrix the local coordinates into global coordinate system, and that can be used directly for the analysis, that is by direct stiffness method. Of your last unit, analysis of structures by direct stiffness method, that is by using this principle of contragradients and converting the member or element stiffness matrices which you have already developed into global one, so you can do the analysis. So now in unit 3 and 4, using this DM equals RTDS as well as this, you can just do the analysis of continuous beam, rigid plane strain and stresses. So independently for any problem or plane strain problem, and you can do the analysis. Later on in the last unit, I can convert similar to element stiffness matrices. Using this relationship, I can develop KS, global stiffness matrix, and that I can use straight away for the analysis. So with this, the unit 1, unit 2, the fundamental or basic knowledge I have derived. So from next class onwards, using these two relationships, that is, and also this transformation matrix, that is rotation matrix, which I told force transformation matrix, using this transformation matrix approach, how to do the analysis of the frame or plane frame structure, we will do from next class onwards. That's unit 3 and 4. One by stiffness method, another by flexibility method, and in the last unit, using that relationship directly, that's called direct stiffness method, how to do the analysis. So from next class onwards is only problems. I will take up directly bar problems, swing problems, beam problem, continuous beam problem, rigid plane problems. That's all we have in your syllabus. That too orthogonal fields only, one by one problem or two problems we will try to solve it and do it.